Hello, I am JD and you are listening to The Ongoing. Today, X rays are almost routine. A broken bone, a dental checkup, a chest scan. Stand still for a few seconds, and the doctor can see straight through your skin to what's happening underneath. But in 1800s, none of that existed. If something was wrong beneath the skin, a doctor could press on it, listen to it, ask where it hurt, and guess. Anything more certain meant cutting you open to look. And surgery back then carried real risk of its own. Then came X rays. This episode is the story of how X rays were discovered almost by accident and how we engineered that accident into a machine that changed medicine forever. In 1895, in a laboratory in Germany, a physicist named Wilhelm Röntgen sat down to run an experiment. Röntgen was disciplined, private, and methodical, the kind of scientist who trusted careful and repeated observations. He was studying something physicists across Europe were excited about: a vacuum tube. Picture two metal plates sealed inside a glass tube with almost all the air pumped out. Apply a strong voltage across them, and something happens inside that tube. At that time, nobody could say exactly what. That is what Röntgen wanted to understand a little better. One evening in November 1895, he wrapped the tube in thick black cardboard to block any ordinary lights from escaping and darkened the room completely. But across the room, a fluorescent screen began to glow. He switched the tube off. The glow vanished. He switched it back on. The screen lit up again. He tried it once more, same result. Something invisible was leaving the tube, crossing the room, and making the screen glow straight through solid cardboard. Röntgen began testing it, placing paper, wood, books, and pieces of metal between the tube and a photographic plate. An early kind of film that darkened wherever the invisible rays struck it. Different materials blocked the mysterious rays differently. Then he tried something extraordinary. He placed his wife's hand in the path of the rays. When the photographic plate was developed, it showed the bones inside her hand and her wedding ring. For the first time, Someone had photographed the inside of a living human body without making an incision. Because Röntgen did not know what these mysterious rays were, he called them X-rays. X meant unknown. So, what was actually happening inside that tube? Today, we know the two metal plates were wired differently, one negative, one positive. The moment the voltage was applied, the electric field pulled electrons right off the surface of the negative plate. That voltage difference pulled those electrons across the tube faster and faster toward the positive plate. Racing through nearly empty space with nothing to slow them down, they slammed into that plate at tremendous speed. That is what Röntgen was studying without knowing. Streams of electrons, tiny negatively charged particles, accelerated by the voltage until they carried a tremendous amount of kinetic energy, the energy of motion. Think about a car traveling at high speed. When you slam on the brakes, the car slows down, but its energy does not simply disappear. Much of that energy is converted into heat in the brakes. Something similar happens inside an X-ray tube. The fast-moving electrons slam into a metal target. Most of their kinetic energy is transferred to the metal and becomes heat. But sometimes an electron passes close to the positively charged nucleus of one of the metal atoms. That nucleus pulls strongly on the electron, causing it to slow down and change direction. And here is the important part. Energy cannot simply disappear. Physicists call this the conservation of energy. One of the most fundamental rules in all of science. Energy can change form, moving from motion to heat to light, but it never just vanishes. As the electron slows down, it loses some of its kinetic energy. A portion of that lost energy can leave the metal as electromagnetic radiation, an X-ray. Here is the whole chain, start to finish. The applied voltage pulls electrons off the negative plate. Those electrons accelerate across the tube. They slam into the far plate. Most of that energy becomes heat. A small amount does not. It comes out instead as an X-ray. That is what was happening inside Röntgen's tube. But how could these X-rays pass through cardboard and through a human hand? X-rays are part of something much bigger, a family called electromagnetic radiation. Visible light belongs to the same family. So do microwaves. And so does something you already know from an earlier episode: radio waves, which carry very little energy, stretched into long waves. X-rays sit at the opposite end of that same family, far more energy packed into much shorter waves. That extra energy is exactly what lets X-rays pass through soft tissue, skin, fat, muscle, almost as if it were not there. Bone is different. It is denser and it contains calcium, which interacts with X-rays much more strongly than soft tissue does. So a lot of the X-rays hitting bone gets absorbed right there and never make it through. That difference, soft tissue passing X-rays through, bone holding more of them back, is exactly what creates the contrast in the image. Here is how it actually gets captured. On the other side of your body sits a detector, or in Röntgen's days, a photographic plate. Wherever X-rays make it all the way through, they strike that detector and darken it. Wherever bone blocks most of them, that spot stays pale, almost white. So the picture is not really a photograph of your bones. It is a map of where X-rays got through and where they did not. Bone shows up white because it blocked the most. Soft tissues shows up dark because it let the most through. And that's exactly what a doctor is looking for with a broken bone. A healthy bone shows up as one solid, unbroken white shape. A fracture shows up as a gap or a shift in that shape, a place where the bone should be continuous and suddenly it is not. Within months of Röntgen's discovery, doctors were experimenting with X-rays to examine fractures and locate bullets. But producing an image in a laboratory was one thing. Building a machine a hospital could control and use reliably every day was something else entirely. From here, the story becomes engineering. Turning Röntgen's accident into a machine a hospital could run every day meant solving one real problem after another. Reliability came first. Early X-ray tubes were unpredictable. They needed a steady, controllable source of electrons. Engineers found it in a heated tungsten filament, which gave off a reliable stream of electrons whenever the tube needed one. Now, the flow of electrons and the X-rays that came from them could be controlled precisely instead of left to chance. Then came heat. At the far end of the tube sat a metal target, usually tungsten, chosen because it would survive extreme temperatures. It had to. Remember, more than 90% of the energy hitting that target becomes heat, all concentrated on one small spot. Fire billions of electrons at the same spot again and again, and it would eventually crack or fail. Engineers solved it by making the target spin. As it rotated, the electrons kept striking a fresh patch of metal instead of burning through the same point, spreading the heat out and letting the tube run at far higher power. Speed was another problem. Early exposures could take minutes, and the smallest movement blurred the image. Better tubes, stronger power supplies, and more sensitive detectors eventually brought that down to a fraction of a second. And eventually, digital detectors replaced film entirely, putting the image on a screen almost instantly. Engineers took the same core idea even further. In a CT scanner, an X-ray tube and detectors rotate all the way around the patient, gathering measurements from every angle, which a computer stitches into a full three-dimensional picture. And there was one more problem. Harder to see than any of the others. Safety. Because X-rays were invisible and painless, early researchers did not understand their danger. Some repeatedly exposed themselves while experimenting with the new technology. Over time, it became clear that X-rays could harm living cells. That risk never fully goes away. It gets managed instead. Modern systems are built around that lesson. Lead shielding, beams narrowed tightly to the area being examined, and the lowest radiation dose that still answers the medical question. The discovery that began with a curious physicist in a dark room eventually earned him the first Nobel Prize ever given in physics. And true to who he was, he gave the entire prize money away, refusing even to patent what he had found. Röntgen never set out to change medicine. He was a physicist in a dark laboratory studying something he did not understand. He noticed a screen glowing when it should not have been. He could have ignored it. Instead, he asked why. That question revealed a new form of radiation. Scientists learned how it worked. Engineers learned how to control it. and doctors gained something humanity had never possessed before: a way to look inside the living body without opening it. Sometimes the biggest discoveries don't begin with an answer. They begin with someone noticing something that should not be happening and refusing to look away. That's it for today. Thanks for listening. I am JD, and this is The Ongoing.